So in the previous lecture, we were discussing about the rigid rotor model of diatomic molecules, but in this lecture, we will be talking about the non-rigid rotor of diatomic molecules. So what exactly is non-rigid rigid rotor model? So here we consider the bonds are not rigid. That's the reason why we call it as non-rigid. So as we know, molecules are vibrating, and as the molecules rotates faster and faster, the bond length decreases. This is due to centrifugal distortion. So here you see there is a set of frequency gaps. This is the rotational constant, and R is the internuclear distance. Okay, so as I go down, you see the frequency keeps on increasing, but the frequency gap is steadily or more rapidly decreasing due to the change in bond length. So you see here till here it's somewhere constant, and then again it's steadily or rapidly changing. It's due to the change is due to its bond length. But here, this case 2b is normally a constant. It doesn't vary much, but here you can see that it varies a little bit. So here from 20 it changed to 19.82, like it is approximately 20, but then there is variation. So this slight variation is due to the internuclear distances. So the question arises is why energy difference decreases with increase in the J value. So I would like to recapitulate whatever I told you now. We can say that molecules is not strictly rigid, as we can see that the bond length increases with rotational quantum number. And so more accurate description of the diatomic molecule is to consider them as a non-rigid rotors. So like we can consider the atoms are connected like a spring, like as it rotates it experiences centrifugal force. As the speed increases, the J value increases, nuclei are thrown outside by a large centrifugal force. It results in decrease in the value of the rotational constant, and we know that if bond length is larger, the moment of inertia is proportional to the square of the internuclear distances. So this is what I was trying to explain. I'll just write these points down so that it will be easier for you guys to understand. So now we'll write the frequencies equation. Nu J for rigid rotor model was Bj into J plus 1, but in case of minus D into J plus 1 the whole square. So this one over here, the D here is nothing but the centrifugal constant. So these terms, centrifugal constant. So these terms was for rigid rotor model, and this whole thing is for non-rigid rotor model. Okay, so let's understand the origin of this equation. Now consider a diatomic molecule which is rotating about a center of mass. So there's this one mass m1, there's mass m2, it is rotating about its own center of mass axis, and then and it is also rotating with an angular velocity omega. We can consider it as a single particle of reduced mass nu. So we can write nu to be equal to m1 m2 divided by m1 plus m2, and the centrifugal force for this equation for this setup is nu v square by r. Omega is equal to v by r, so we need a square here, so we can write omega square. So into r divided by r, we'll get this like this. And the restoring force F of r is equal to k r minus r naught, where k is the force constant, Fc is equal to Fr at equilibrium, and so we can rearrange and write omega square r is equal to k r minus r naught. R minus r naught is equal to nu omega square r by k. So now what we're going to do is we're going to find the total energy. In case of a rigid rotor model, if you remember, we only consider the kinetic energy part. It was half m1 v1 square plus half m2 v2 square, and we found the equation. But here for non-rigid rotor model, we are using the kinetic energy as well as the potential energy. So the kinetic energy here is half m omega square, and potential energy is half k, the restorative force, k r naught, r minus r naught the whole square. So r minus r naught is nothing but this one over here, nu omega square r by k. So it will be half I omega square plus half k nu square omega raised to 4 r square by k square. So this k get cancelled, you'll get by k. Yes, okay. Next, so from here we know that I is equal to nu r square. So I square is equal to nu square r raised to 4. So it's only square here, so we'll multiply and divide by r square. So what you'll get next is half I omega square plus half, so it will be I square and omega raised to 4 is there. So I omega square the whole square divided by k. Kr square, yeah, sorry, yeah. So next one, we know that L is equal to I omega, right? There is, if you multiply and divide by I, you will get L square. So half L square by I plus, same thing here, it should be square here, so I square, and I just think, so if I multiply I square, it will be L power 4 divided by 2 I square. I have to multiply and divide, no, so I square by there in the denominator and kr square. Okay, now we know that L is nothing but h cross j into j plus 1. So these things we know. L is equal to I omega, I is equal to nu r square, and L is equal to h cross j into j plus 1. These things we know. We just have to substitute while we solve. So half h cross square j plus 1 by I, and this one will be same thing. So it will be h cross square j plus 1 the whole square. Sorry, this is h raised to 4, sorry, yeah, divided by 2I square kr square. Now h cross can be written as h by 2 pi. So half, this is square, so it will be h square by 4 pi square, and there's a 2 here, so 2 into 4 is 8, so you can write 8 pi square j into j plus 1 divided by I plus h cross square by 4. So h raised to 4 divided by 2 raised to 4 is 16 into 32, so 32 pi raised to 4 I square j plus 1 the whole square divided by, okay, k square. Yes. So let's write in terms of nu j. So nu j is nothing but Ej divided by hc. So this terms Ej, okay, you have to multiply by hc. So into hc you will get, divided by hc you will get this, okay, 1 second, the divided by hc, this gets cancelled, so, and here also 1 hc, this will be h cube, and you will get a c in the denominator. So I can resubstitute the value of I is nu r square, so I'll just write it back. So h by 8 pi square nu r square c j into j plus 1 plus h cube 32 pi raised to 4 nu square r raised to 4, sorry, this will be r raised to 6 because there's a square here to c, j into j plus 1 the whole square, right, yeah. Okay, now what we're going to do is that so the first term is proportional to r raised to minus 2, and the second term is proportional to r raised to minus 6. Since the centrifugal distance changes with the bond length by small amount, the second term can be replaced, the r from the second term can be replaced by minus r naught. So the equation changes to r naught power 6, and that's a minus here. Yes. So this term over here, this one is nothing but b. So I can rewrite this equation to be equal to b j plus 1 minus h cube j plus 1 the whole square divided by 32 pi raised to 4 nu square r dot raised to 6 kc. So as I said, b is equal to h by 8 pi square nu r square c. Just like that, nu is equal to 1 by 2 pi c k by nu. So on substituting these values, we can simplify this equation. I can simplify this equation and write it like 4b cube by r naught square j into j plus 1 the whole square. So after substituting this and this into this equation, we'll get like this form. Okay, so finally I can write nu j is equal to b j plus 1 minus 4b cube. So this was cube, 4b cube divided by r naught square j into j plus 1, and this one over here, this term is nothing but d, centrifugal constant. Okay, so finally I can write nu j is equal to b j plus 1 minus d j plus 1 the whole square. Yeah, and maybe I can simplify more. I can take the j plus 1 term common. So j into j plus 1, I can take it common. I'll get it as b minus d j plus 1, and this one over here I can write it as b effective. So the formula simplifies into b effective is equal to b minus d j plus 1. So this is a simplified equation. You can stop at this stage itself. Now next what we're going to do is we're going to find the frequency gap. So del nu j is equal to nu j plus 1 minus nu j. So this one is b j into j plus 1, right? Minus d into d j plus 1 the whole square. So this one is b j, I'll write it here, b j plus 1. Okay, there was this j plus 1 j plus 2 minus d j plus 1 j plus 2 the whole square. Yeah, so there is this minus here, and yeah. Okay, now to solve this equation. So I separately wrote b terms together and d terms together. Now you can take b j plus 1 term common from here, and the rest of the term is b j plus 2 minus j. Similarly, you can take d j plus 1 the whole square, and the rest of the equation will be j plus 2 the whole square minus j square. Okay, so this one over here, j gets cancelled, so you will get 2b j plus 1, and over here d j plus 1 the whole square. Yeah. Okay, so if you open this bracket, you will get j square plus 4 plus 4j minus j square. So this is cancelled, you will get 4 common j plus 1, right? So 2b j plus 1 minus d j plus 1 the whole square, 4 common j plus 1. So finally del nu j is equal to 2b j plus 1 minus 4d j plus 1 the whole cube. So this is the frequency gap. So that's it for this video. We have completed non-rigid rotor approximation. See you in the next one.